This is Miss Clark with 1.2 linear measure. We're going to start here with a definition. Hopefully you've seen this definition before in your vocab. We're going to go over it again. This is the definition of a line segment, which most of the time we just refer to as a segment. And this definition says if a line is a segment, then it consists of two endpoints and all of the points in between them. So I'm going to have one endpoint here, another endpoint somewhere else, and then everything in between them is just going to be a line that connects these 2 points. Alright, and then in general, when we have a segment, we are going to label it with endpoints, or it will have endpoints already labeled. I'm going to call this end A, and I'm going to call this end B. So when we talk about notation, or how we write segment AB here, we would do a straight line over the top, and then we would say AB. And this notates that I have a segment AB. Now when we're talking about the measure of AB, so if we were talking about, say, the length of this segment, we would just use AB without that segment on top. So just be like the two letters together, and then we could say like AB is equal to 3 or something like that. So in general, when we're talking about this length or the measure of the segment, we just leave it in this form, and then we're talking about the segment itself, then we're going to have that line, that straight line over the top of it, or that segment over the top of it, really, because it's finite and doesn't go on forever. Okay. So now we're going to talk about betweenness of points. I think the importance about this definition is really focusing on what does it mean to be between when we're talking about segments. So this definition says point M is between points P and Q if and only if P, Q, and M are collinear and PM plus MQ is equal to PQ. So let's break this down. What is it saying? So I have points P and Q. And then it's saying that M is between points P and Q. And I think if we were just thinking about the word between as a general term, we would maybe infer that M could be really anywhere that's sort of in between any of these points. But when we're talking about the definition of between, as it refers to a line segment, between is always going to be directly on this line. So that's where this collinear comes in. M is collinear with P and Q, so they share a line. So this is going to be my point M here. And then we can sort of clearly see that this statement down here has to be true. If M is on this line PQ, then this point PM, or the measure of this segment PM plus the measure of this segment MQ, when we combine them together, it's going to give us that whole segment PQ. So for instance, if I knew that the measure of this little distance right here was 5, of PM was 5, and I knew that the measure of MQ was 3, then PQ would be 8. So since PM plus MQ is equal to PQ, then 5 plus 3 is equal to 8. And again, you'll see that we're talking about the measure or the length of these segments, so we don't have a line over the top. We're just talking about this measure of this segment here, and the measure of this segment is equal to the measure of this segment. Okay, and finally we're going to talk about congruent segments. So I want to define congruent segments, and then I want to talk a little bit about what congruence is and why we use the term congruence. So I've got my definition here of congruent segments. It says if two segments are congruent, then they have the same length. So another way we could think about this is if I have two segments that are congruent, if I were to take this segment and rotate it so it lines up with this other segment, I could place it exactly on top, and it would be pretty much the same exact segment. So they don't have to be in the same direction. They can really go any which way you want, but the important thing is that they would always map directly on top of each other. And so we mark these. When we say two things are congruent, we usually use a dash. Sometimes you can use more than one dash, but usually we'll use a dash on each segment to notate that both of these are congruent to each other. And then I'm going to label these with endpoints so we can talk about this notationally. So I'm going to call this first segment AB, and I'm going to call the second segment CD. So notationally, when I'm talking about my segments, I would say segment AB is congruent to segment CD. So here's the key. This little equal sign with my little tilde or my squiggly on top, this means congruent. And then it's also saying that they have the same length. So not only could we talk about this segment being congruent to CD, but we could also say that their lengths are equal. So my length, oh sorry, that's too big. My measure of AB, which is just my two letters without the line, is going to be equal to my measure of CD. So here's the biggest difference about congruence and equality. So when we're talking about, they do sort of mean the same thing in that it means that the one is the same as the other one in terms of length. So why don't we just say that segment AB is equal to CD? Well, we use the terms congruent and then equal to differentiate whether we're talking about a shape or whether we're talking about an actual size. So we're going to use the term congruent when we're talking about relationships between figures. So this is going to be when we're talking about different shapes. So I would say that a triangle is congruent to another triangle, or a segment is congruent to another segment. And then we use equal when we're talking about the relationship between sizes. So in general, that's going to be when we're talking about numbers. So this would be like 3 is equal to 3, or the length of AB is equal to the length of CD. But the segment AB is congruent to the segment CD. So that's the biggest difference between congruence and between equality, is just if we're talking about the shape itself or we're talking about the size of the shape. Alright, and then finally we're going to end with an example. And this is going to show us really what we're going to use this information for and how we're going to use it to solve problems. So I'm going to read the problem, and then I'm going to go through the problem and use the information it's giving me to sort of construct a diagram. And then once I construct that diagram and label it, I'll be able to solve this and figure it out. So it says find x and bc if b is between a and c, and AC is equal to 4x minus 12, AB is equal to x, and BC is equal to 2x plus 3. So right now we know that B is between A and C. And from our definition before, we know that that means that it's not just somewhere hanging out in the middle, it's directly on the line AC. So I'm going to have a line AC, and then B is going to be directly on this line somewhere in between A and C. And so now I'm going to label these different parts. So I have AB is equal to X, and AC is equal to 4x minus 12, and then BC is equal to 2x plus 3. And now I can use my definition of betweenness of points, because I know from that definition that AB plus BC is equal to AC. So I'm just going to replace each of these measures with their values that we were given in terms of x. So AB is equal to x, BC is equal to 2x plus 3, and AC is equal to 4x minus 12. And now that we have just one equation with only x's and numbers, we can solve this equation for x to find our x. And then once we have x, we can go back and find our BC. But we've got to find x first. So I'm going to combine like terms, and I get 3x plus 3 is equal to 4x minus 12. And then I'm going to move my variables to one side by subtracting 3x. And then I'm going to move my numbers or my constants to the other side by adding 12. And then I get, let me get a different color. So these cancel and these cancel, and I get 15 is equal to x. So I've solved that first part. I know that x is equal to 15. And now I want to find BC, so I want to find this length right here. Oh, sorry, I didn't mean to do that. So now that I want to find this length BC right here, I'm going to plug in x into this because I know that BC is equal to 2x plus 3. So I'm going to take my 2x plus 3, and then I'm going to substitute x for 15 and do 2 times 15 plus 3 is 33, and this is equal to my measure of my segment BC.